Okay, so good evening to all of you. Am I audible? So good evening to all of you. Am I audible? Okay, thanks, Alex. So we'll wait for some few minutes and let's see if others join. Then we can start. So kindly wait for some time and then we can start the session. So thank you. Okay then, I guess we can start. So first of all, I would like to welcome all of you to this course. That is Fluid Mechanics and its Applications, taken by Professor Vijay Gupta from IIT Delhi. And uh, since this is the first session for this course, it will be just an interactive session or just interactive session, and we'll just go through the brief overview of what Professor Gupta has discussed in his week 1 lectures, and just go through some of the basic concepts, get clarified, and let's try to tackle some of your doubts if at all they may occur. And from the next session, we will go on to solve some problems which will uh, which are ought to occur. So we will try to solve them. But for the first session, we are not dealing with any kind of problems right now, because I think it would be wise enough just to deal with the concepts for the first session at least. So just you can just intervene at any time, like if you don't understand anything, or if my voice breaks out somewhere, so that there is no hindrance in understanding of the concepts, right? So you can just stop me whenever required and just ask me what part you didn't understand. Okay. So okay, as the name of the course itself suggests, it is an application based course. So no doubt at all that we will cling ourselves to the basic concepts of fluid mechanics, and we cannot go away from them. But yes, but we will fundamentally try to understand the applications of these concepts that we learn from this course, and try to see how the concepts that we have learned from this course are applicable applicable in our day-to-day life, and try to understand these applications and try to solve problems related to them. So this is the basic objective of the course, but still we need to deal with some basic concepts. So let's go through it uh, as we can. So as it is mentioned, the learning objectives of this course are fundamentally deals on the principal concerns of the subject of fluid mechanics. There is basically the basic concepts starting from the no slip boundary conditions to the continuity equation, momentum equation, Navier-Stokes, like this. We will deal with them and try to understand the applications in our day-to-day life. Okay. Then the distinguishing property of fluids, at least for the first lecture that deals with the fluid and its properties, we will try to understand the distinguishing property of fluids, like how fluids are different from solids, what are the characteristics that distinguishes fluid from a solid. And then finally we will deal with a very important law or rule, you can say, that governs the motion of fluids, that is the Newton's law of viscosity, that, that relates the stress generated in the flow field with the strain rate, okay, and in this case the velocity gradients that will eventually look through. So that's what we are going to do. Okay, so as Professor Gupta might have or obviously mentioned in the lectures, that a fluid applies forces on an object whenever it moves past them. Basically means that if you put an object in a fluid flow, it will experience some kind of force, right? Or conversely, we can say that if we want to move that object in a fluid, in a stationary fluid, say, or even in a moving fluid, if we want to move that object, we have to apply some additional external force so that we can overcome the resistance that is being offered by the fluid. And this resistance that you will eventually understand is because of the viscosity of the fluid, right? So okay, and we will also look through some of the examples. We'll also look to some of the examples where the fluid motion modifies the rate of heat transfer. Even though this will not be our primary concern for this course, because a separate course known as heat transfer deals with such kind of problems. That is basically how the heat transfer rates are modified because of the motion of fluid, and fluid then it may constitute of any it constitutes both of air and air and liquids. So that's both constituted that gases and liquids, so both are constituted as fluids. So it is basically heat transfer that deals with such kind of problems. But still we'll look at some of the examples which deals with these concepts. Okay, so then we will basically discuss about the various forces in fluids. Okay, so first is buoyancy force. So basically I will not go through every detail of the concept that was that was discussed by Professor Gupta, because it would be wise enough for every one of us to look at the lectures, because those are the fundamental resources for us to learn and the best resources. So I would suggest that to every one of you. But still, if since I told that it would be a slightly interactive session because it's the first session, so could any one of you please tell me what do you mean by buoyancy force? You can please unmute yourself and just mention a very simple definition. I don't need much complicated long definitions. A simple definition. What do you mean by buoyancy force? Yes, please. You can say, you can try. If it's wrong, that's completely fine.
So an upward force exerted by fluid.
Okay. So who was it actually? I couldn't see. Who was it?
Sir, me, Afridi answer.
Oh, thanks, Afridi. So that's correct. An upward force exerted by the fluid on a body that is being submerged in the fluid, right? So that's absolutely correct. So this is one of an example of force exerted by a fluid on an object, right? So I guess everybody understood it. And then there is a pressure force, and we'll eventually see that this these are the forces that act normal to the surface of the body. Okay, for example, say there is a surface, say a spherical surface. So I will just do a cross section of it, and say, like, if we want to look into an elemental surface area, say this is a small elemental surface area, and this is the area vector of that normal vector of that elemental area. Okay, so could anyone you please tell me, like, if there is a fluid, say okay, So if there's a fluid existing on the outer periphery of this spherical object, say, right? So along which direction, with respect to this normal vector of this elemental area, the pressure force would act? Could any one of you please tell me the direction of this pressure force with respect to this area vector?
Sir, parallel.
Parallel in the sense like would it act say in this direction or in this direction, like opposite to the direction of the area vector, or like along the direction of the area vector?
Sir, opposite.
Okay, so that's absolutely correct. So you will eventually see that whenever we deal with pressure, it is found that the pressure always acts in the direction opposite to the outward normal vector to a elemental surface area, right? Now say you may say that if we are dealing with a fluid inside the area, inside this spherical surface area, say if the fluid was, instead of being outside, the fluid was inside, say within this spherical shell, right? So the, okay, I will just draw a, okay, so like this, like the thickness of the spherical shell be shown. So if the, if we wanted to calculate the force acting on the inner surface of, sorry, to calculate the force acting on the inner surface of this spherical shell, so obviously the, okay, so obviously the area vector, okay, let's not deal with this, think along in that direction, we'll eventually come to that. But say like if the fluid is I'm sorry, so if the fluid is inside this spherical shell, you may say, you can rightly point out that the pressure would act in the outward direction, right, from the center of the spherical shell towards the outward direction, if the fluid is pressurized within this spherical shell, right? And so you may say that now if you were to choose a surface area or the surface on which this pressure force would act, you which would be the surface of our concern in this case, the outer surface or the inner surface?
Inner surface.
Yes. So as you rightly pointed out, if it's the inner surface, then the elemental area of our concern would be within, would be in the inner surface of the sphere, and the normal vector of this area outward to this area would be pointing towards the center of the sphere, right? And in this case also we can clearly see the pressure force would act opposite to the direction of the outward normal vector of the area of our concern, right? So you can clearly see that the pressure force always acts in a direction opposite, though it is parallel, but it acts in a direction opposite to the direction of the area vector to the surface along on which we are trying to evaluate the pressure forces. Okay, so one of the applications, yes, since it's an application based course, we will Professor Gupta has rightly discussed applications for all these kind of forces, right? So one of the examples that he has discussed for pressure forces was the hydraulic brakes used in the cars. So for the detailed explanation, I suggest that you look back to the lectures. Like there are very good animations shown by Professor Gupta, so it will make your concepts very clear. And eventually in the later part of the course, we'll deal with some problems that will help to clear your concepts regarding this. So right now I would just suggest that you just look into the videos or animations that show the working principle of this hydraulic brakes, so that you can just have an idea of how these hydraulic brakes operate, or how the pressure forces come into picture in these hydraulic brakes. Okay, so I would suggest that. Then comes the drag force, right? So the force opposing the motion of the object, right? and you will eventually see that these drag forces act along the surface of the object. So we will eventually discuss that when we are discussing about flow past immersed bodies, right? It's a particular chapter in this course, or the fluid mechanics course, that flow past immersed bodies. So we will clearly understand what's the drag force and lift force, and both are slightly discussed here, but the actual direction of these forces, how they act, and what are the implications on the forces acting on the object, we will eventually discuss when we reach that chapter. But still, just to give an overview, like there's a drag force that acts along the surface of the object that tends to slow it down, right? That tends to oppose its motion, as rightly pointed out by Professor Gupta, that oppose the motion of the object. Like if an object is say this is an object and this is moving in this direction with certain velocity, our drag force will act opposite to the direction of the opposite to the direction of the motion of this object, that will tend to slow it down. Okay, and one of the positive applications, as I was positive applications, because in most of the cases these drag forces are an unnecessary force that we need to overcome, right? For example, in the case of racing, like race cars or Formula 1 race cars, you will eventually understand that these Formula 1 race cars are designed in such a way that they are as much streamlined as possible, so that they could overcome the drag that is acting on them. And this drag can be of two types, that is the skin friction drag and the form drag, that will eventually discuss. But still, the very design of these Formula 1 race cars are made in such a way that they could overcome these drag forces, so that they could finish the race or cross the finish line as fast as possible. So drag forces in these cases are extremely unnecessary force. But still, one of the positive applications of these drag forces that come into our day-to-day life are parachutes, right? The life-saving these are life-saving equipments, or equipments used to as discussed by Professor Gupta. These parachutes are also used to transfer payloads from a satellite or an aircraft from a higher altitude to the surface, right, to the ground surface. Like if you want to transfer some payload where the plane cannot land, but it can release the objects or the load from the planes to the destination where it want to where it wants to be the object to be reached, with the help of parachutes, right? Because then this parachute, the drag forces acting on these parachutes would help to slow down the motion of these parachutes, and thus protecting the payloads that is being attached to the parachutes, right? So it will not allow the object to be destroyed because of the fast motion of these parachutes. So I guess the concept was clear, because I guess all of you really know what a parachute is and how it fundamentally works, right? But still, the application of the drag force, how it is related to parachutes, that we discussed briefly. Okay, then as I discussed, if there's a drag, there's always a lift force, and a lift force is a type of force that acts normal to the direction of relative velocity, right? So one of the fundamental or the most popular applications of the lift force that you listen, like you may always listen in day-to-day life, is in aircrafts, right? As I as I have written here, the flying of aircrafts are fundamentally are based on the fundamental principle of lift generated due to the motion of these aircrafts through the wind, and these are achieved by the help of some special design of the wings known as the airfoil. And how if I talk about airfoil, then it's a specially designed shape that I'm sorry, that helps in generating lift when it is forced to move past and move through the air, right? So for example, like if the if the airfoil is stationary for right now, and the fluid is moving across it with certain velocity, say v, so because of the shape of the airfoil, you will see that there is a low pressure area generated on the upper surface, low pressure on the upper surface, and a high pressure region generated at the lower surface of the airfoil. And it is this pressure difference that generates the lift required for the aircraft to take off and thus move with the cruising velocity so that it could go from one place to another, right? So this is the fundamental concept, and this pressure, high pressure and low pressure, how they are created, I must say is a very in simple words, very interesting concept of an interesting concept, and like quite difficult to be told as an introductory in the introductory session for any course. So I would leave this part right now, but basically it means it is because if I had to say, because of the shape of the airfoil, and the shape of the airfoil causes the velocity of the wind on the upper surface to be higher, say V upper, than the velocity at the lower surface, and this velocity difference generates a net pressure difference between the upper and the lower surface of the airfoil, which thus generates the required lift. Okay, so okay, and another example of this lift, as discussed by Professor Gupta, was an outswinging ball in cricket. So I guess most of you, or I must say all of you, know what an outswinging ball is in cricket. All of you watch cricket, so you know what an outswinging ball is, and how the the initial swing given to the ball generates a force. If I draw it, so if this is the ball, and say this is the initial trajectory applied to it by the bowler. So an outswinging ball, like as discussed, is basically like you give an initial swing to the ball that would generate a certain rotation of the ball in its initial stage, and thus this rotation would lead to a trajectory, like it would lead to a sideward force normal to direction of motion of the ball, and thus this side force would result in a ball to go a trajectory sideways compared to what it would have gone if the initial swing was not given, right? So this is the concept of an outswinging ball in cricket, and how the lift acts in these cases. One of the other example would be the Magnus effect, and okay, I guess this was not discussed, but still I would like to discuss, at least let you know about it, the Magnus effect. So this effect is primarily seen in or the most fundamental application of Magnus effect in sports, if you may say, is seen in football, right? Say you may see some very famous footballers curling the ball past the goalkeepers, like the ball, say if this is the goal post, and like if the ball is being hit by the player here, so you may see that the ball takes a very peculiar trajectory, curls past the wall of players and goes inside the net. So this curling motion is also because of the application of the fluid mechanic concept of Magnus effect. But it may happen that the footballer may or may not know about it, but still this is a very important day-to-day life scenario where we can see the Magnus effect in action. Okay, so and there are then oscillating forces, and these forces are like I must say a much more complicated forces to be understood at the initial stage, but still one of the examples that had been discussed by Professor Gupta was the, if I may recall, was the uh, failure of a suspension bridge in some city in US, I guess. So it was seen that the bridge failed even if the velocity of the air moving past the bridge was not that high or not that catastrophic that would lead to such a big damage that would eventually lead to the breaking of the entire bridge, right? So why did this happen? It happened because the oscillations the oscillations generated because of the wind moving past the bridge. Say, I would like to explain it through a diagram. It's difficult to be told, difficult to be uh, told without the help of some illustrations. So, say this was the bridge, and say these are the pillars that supported the deck. I must, if I'm not wrong. So, okay. So this is the side view of the bridge, okay, and you may say that the wind is moving past in a direction to inside this page, say perpendicular z direction, say this is x, y, and z, right? So towards the negative z direction, you may say the wind is blowing with certain velocity. So v is equal to 60 meter per second. See. So, according to the engineers, this velocity was not catastrophic at all. Like, it was a velocity that could have been easily handled by the initial design of the bridge. But the engineers failed to take into account one very important design perspective that's known as the resonance, or the natural frequency, or related to the natural frequency of any object. See, natural frequency is an concept that could be applied to any object, right? Everything starting from a microscopic object to things as large as the bridge, or even things larger than it, has its particular natural frequency, has a natural frequency. And the concept of the concept of resonance states that if an external oscillating force is applied to the object, and if the frequency of this external oscillating force coincides with the natural frequency of the object, the displacement that occurs due to this oscillating force would be very high, that would result in the failure of this object. Like, see, if I zoom it in, so say if I had to zoom in this area, so say this is the cross section of the bridge, and if I zoom it in, you will clearly understand that the wind would move like this, right? And in the lower surface like this. So in a simple manner, if I try to make you understand, this motion, this curling motion of wind, okay, so this curling motion of wind past the deck of the bridge would result in certain small slight displacement, maybe a slight displacement from its initial position, okay. Similarly, this this motion of the wind from the downward part of the deck, when it moves past it, it will again result in certain displacement from its initial position, okay. That's bound to happen. Like, it may not be perceived by human eye, but that's bound to happen, and that naturally occurs. Like, that can be, if you want to observe it in a day-to-day life, like, you may see it in the case of leaves, right? The tree leaves. Like, when the wind moves past the tree leaf, you can see that the leaves try to oscillate violently, right? When the wind moves past the leaves, you can see that the leaf would the leaf would move violently from its initial position, right, and it's all because of the motion of the wind past the leaf, right. That's causing the leaf to flutter, right. Similar to that case, there are very slight displacements that occur due to the motion of the wind past the deck of this bridge, right, and that are completely within the design perspective, or the within the factor of safety of the design of this bridge, right. But if this if the frequency of the oscillations that is being caused due to the motion of the wind coincides with the natural frequency of this object, right, of this deck, say, it would result in a very violent oscillation that is much larger than the initial oscillation. That is, if initially the displacement was very small, if the frequency of oscillations due to this external force matches the natural frequency of the deck, it will result in a very violent oscillations from its main position, and which would thus result in the failure of the bridge, right. And that is what exactly happened in that case. So as I guess Professor Gupta again pointed out, to rectify it, the engineers, after the failure of the initial bridge, they tried to create a bridge that was much stiffer than the initial design. That basically, I may say, maybe reinforced the deck within in every span, like this is the span of the deck. They might have reinforced the deck within in certain areas, so that the stiffness of the deck increases, and thus the natural frequency goes up, right. So I guess that was the way by which the engineers handled this critical problem. And again, some other examples, it is human vocalization. Like, it's also one of the applications of fluid mechanics, of how the motion of air through our larynx causes the sound to be generated from our voice box, I must say. How the oscillation of that larynx results in different frequency of our voice, that because as a human being we are capable of generating voices at different frequencies, and how this is being generated, like it is basically governed by the oscillation of this larynx. So it has been discussed very nicely with live examples in the lectures, so I suggest you look into that. And okay, then comes swimming. So if we deal with swimming, swimming in itself is a very extensive topic of discussion, like which includes various concepts of fluid mechanics in it. The thrust, the lift, the drag, every kind of force acts upon it, and how it is generated, I guess it would be, it's not the right time to be discussed at the introductory lecture, but still I guess Professor Gupta very nicely discussed it in his lectures. He mentioned it with a very nice drawings showing the direction of the lift, drag, and the thrust. But still, as he also rightly understood, it was not a wise idea to discuss the entire concept of swimming in the introductory lecture. So he just left with some slight overview of the concept. But what's more important for introductory lecture is, I must say, how the motion of a swimmer, like in the case of, say, human beings or animals of similar to the size of our body, say leopards, large rodents, say dolphins, like that. Okay, how the motion of a swimmer. So to simplify the case, I would say I would compare it to humans. Say I explicitly described it. I'm discussing a human swimmer. Okay, how the motion of a swimmer is different from motion of a sperm. And compared to sperm, we also take the example of motion of bacteria. You can also compare it to the motion of bacteria. So what do you think, like, okay, say I'm discussing the motion of a swimmer versus the motion of a bacteria. Okay, so within these two different even the action is same, but a conceptually different topics, what are the different factors that are like, what are the factors that are different in these two cases? Can anybody please point out, like, what are the things that could be different in these cases? Motion of a human swimmer and a motion of a, say, a sperm or a bacteria moving in a certain fluid. Yes. So could anyone point out what can be differences? There are obviously differences, some very obvious differences. I just wanted to know that. What are those obvious differences? Please, I guess it's very simple question. How is the, yes,
Friction, viscous force will be less on
on?
human swimmer.
Okay, okay. I guess you're reaching on far more advanced topics. I'm not going up to that. Like, obvious difference. What is the obvious difference between a human swimmer and a bacteria? Rather than going to viscous forces, let's say, what are the visible differences that you're able to see between a human swimmer and a bacteria? For example, let me say the size. It's an obvious difference, right? The size, if I denote it with, say, length, right? The length scale would be a better term. The length scale is vastly different. Say, length scale of the human is much greater than the length scale of a bacteria. Okay, this is one obvious difference. Anything other than that? Think about the distance the human swimmer covers in a single stride compared to the distance covered by a bacteria in a single motion of their spagellum, or the arm-like structures that a bacteria have. So, see, the bacteria, it will have some structures that it uses to propel in the fluid. So, say, is there a difference between a distance covered by the human swimmer and the bacteria? So it's obvious, it is obviously there. So, and this distance could be correlated to the velocity with which these swimmers move, right? So I would say that the velocity of the motion of the human swimmers are much larger than the velocity of this bacteria, right? So these are the like some obvious differences that are being visible, and you'll eventually see that how this and I guess it was Afridi who pointed it out, if I'm not wrong. So if I'm wrong, I'm sorry. Okay, thanks. So as he pointed out, he discussed about some viscous forces, right? And in the domain of fluid mechanics, these viscous forces are being determined or quantified by a term known as viscosity. Okay, so we were eventually going to discuss that, but since it is pointed out, I would emphasize it. So viscosity. Okay, so here we can see there is a length scale, a velocity, and a viscosity, right? So in the later part of this discussion, you will eventually see that one of a very famous scientist known as Osborne Reynolds, right? He did an experiment which showed that the nature of flow that we'll discuss, that is laminar and turbulent, is determined by a composite parameter made by comprising of the length, velocity, and the viscosity of the length of the length scale, the velocity, and the viscosity of the fluid, right? Viscosity of the fluid in concern, and this parameter is known as the Reynolds number, right? So if you try to if you try and write mathematically, so it would be rho v L by mu, where rho is the density of the fluid. Just Okay, so just wait a while. Okay then, sorry for the interruption. I'm really sorry for that. So yeah, so you can see that we have so if this is the definition of Reynolds number, we have discussed when we are trying to compare the motion of a swimmer and a motion of a bacteria. We pointed out the length scale also came into picture, the velocity as well as the viscosity. So you may think that the density is not coming into picture, right? But in more, as we go further, you may see that a more appropriate way of defining Reynolds number is with the help of the kinematic viscosity. That's basically denoted by nu, where nu is the mu divided by rho, where mu is known as the dynamic viscosity. Okay, so we will again also discuss why the what is the role of kinematic viscosity, or how kinematic viscosity turns out to be a more useful parameter compared to dynamic viscosity, right? We'll eventually come to that, but you can now clearly see how the obvious differences between the motion of a swimmer and a human swimmer and a bacteria helped us to deduce the concept of Reynolds number, right? So I hope this concept was clear, like how we deduce the concept of Reynolds number by the help of, by comparing the motion of a human swimmer and the motion of a bacteria in a fluid. And as Afridi rightly pointed it out, he mentioned that the frictional forces acting on the sperm or the bacteria would be much higher than the swimmer. So I would not say that it is much higher compared to the swimmer, but a more appropriate, or I'm not saying that he is wrong, but more appropriate way of saying this would be that the frictional forces dominate the fluid flow in the case of motion of a bacteria, right? And in the case of swimmer, it is the inertia forces that dominate the motion of the swimmer past the water, right, past the fluid. So in the case of bacteria, you can say if it is bacteria, you can say it is viscous forces dominated, right? And in the case of human swimmer, it is inertia dominated. So, okay, so is it clear, Afridi, like why I'm saying that it would be a better way to say that is, instead of the frictional forces acting on the bacteria being higher, you can say that the motion of the bacteria is being dominated by the viscous forces rather than inertia forces. And in the case of humans, the inertia forces dominate its motion. So is that clear, Afridi?
Yes, sir. Clear.
Okay, thank you. So again, Professor Gupta discussed a single example regarding the how the motion of fluid governs the rate of heat transfer from the object. So he discussed about chimneys in a nuclear plants. So this is one of the example. There can be various other examples. So I would, since I have dealt with the subject of heat transfer, there is a very famous application where the fluid flow determines the rate of heat transfer or governs the rate of heat transfer. That could be the dissipation of heat from the fins, right? I guess all of you know about motorcycles and must have saw some protrusions outside your engine, right? Some such kind of protrusions. Say this is your engine, say the cylinder of your engine. You might have seen some certain protrusions out of its actual surface area, right? And these outer protrusions are known as fins. And what this fins essentially does is increase the surface area through which the heat can be dissipated. And since the bikes or motorcycles are in motion against the existing wind, so wind is bound to flow across it, and this flowing wind, what essentially does is carries away the heat from these fins, which is being taken out from the, like, say, since there's a combustion within the engine, it will obviously generate heat, and for the safety of the engines, we need to dissipate this heat. So these protrusions will try to increase the surface area through which the heat generated from the combustion can be dissipated. And a very effective way of dissipating this heat is by the help of convection. It is basically the heat transfer because of the bulk motion of fluid. So the motion of this fluid past these fins would carry away this additional heat from the fins, these outer protrusions, and thus help in dissipating the heat that could have been detrimental for the engine. Okay, so this is one of the two examples that we have discussed. And finally, he also discussed the efficacy of face mask. And while discussing the efficacy of face mask, I guess the fundamental objective that Professor Gupta was trying to achieve was to let us know about the various flow visualization techniques, right? So in that case, I guess he showed the scleran images. If I'm not wrong. The spelling may be wrong, so I'm sorry. Scleran images. Yeah, these are one of the flow visualization techniques. Okay. Then another may be PIV, or the particle image velocimetry. So these are some of the flow visualization techniques. And the fundamental objective of discussing the efficacy of face masks was to let us know about the different flow visualization techniques, right? Particle image velocimetry. So I will stop here for right now. So just wanted to know, like, there are some more topics to discuss, slightly some basic fundamental concepts. So now, of course, up till now we are just discussing about applications, right? So now we'll just go into a bit about the subject and discuss fundamental concepts. We will not go too that deep, just fundamental concepts related to the subject, right? But up till now, like, I just wanted to know, like, is there any doubt like that up till now what we have discussed?
Yes, sir. I have one doubt.
Okay, sure, please.
About the fin. Okay.
Yes.
So inside the cylinder there is heat generation due to combustion.
Okay.
And outside the fins there is cool air. No?
Yes.
So won't it be conduction instead of convection?
Where?
The air outside and the heat inside the combustion chamber. The heat transfer will be conduction, no?
Yes, you rightly pointed it out. So in the case of heat transfer from the inner surface of the cylinder to the outer surface of the fin, it would be conduction. That's right. But from the outer surface of the fin to the outer air, it would be convection. And if you know, convection is a sum or a combination of both advection and diffusion, right? So in the case of convection, the advection would dominate. That is, the bulk motion of the fluid that carries the heat would dominate, and thus we say that it is the bulk motion of fluid that helps in dissipating the heat from the outer surface of the fin, right? But as you rightly pointed it out, from the inner surface, it is conduction through which the heat is being dissipated from the inner surface of the cylinder to the outer surface of the fin. It is conduction. And if there was no motion of fluid, right, if the bike was stationary and the engine was running, then also there would have been heat dissipation. How? It would be through conduction, right? There is a temperature difference between the outer surface of the cylinder and the outer surface of the cylinder and the ambient air. So this will result in a diffusion of this will result in a conduction that will conduction between the outer surface of the fin and the air, right? But I told that since the air is moving, the convection would dominate, and thus the dominant mode of heat transfer in this case would be convection.
Okay, sir. Got it.
Okay, thank you. You rightly pointed it out. Like, I dropped the concept of conduction because, like, since we're discussing our fluid mechanics, so I just emphasized more upon the role of fluid mechanics in dissipation of heat. But still, it's very nice that we know about conduction at least, how and what role the conduction plays, right? So that's fine. Anyone else, like, there's any doubt? So, okay, I guess that's fine. Even if you have any doubt after the session, you can obviously keep your doubts in the Google form, I guess, the discussion forum in the website. So it is completely fine. We can discuss it there. But still, okay. So now we look into some fundamental concepts of the subject itself, right? The fluid mechanics. So before at all discussing it, it would be very appreciable if anybody of you, like, pointed out what is the fundamental difference between a solid and a fluid. So could anyone please tell? Like, if you don't know, that's completely fine. But if you know, or if you have any faint idea, like, what would be the difference between a solid and a fluid?
Fluid does not resist shear force, while solid does.
Okay, so that's a very, what to say, efficient definition, I could say. Very nice definition, capturing all the keywords that's needed. So as you rightly pointed it out, the fluid would not resist the external force that acts upon it. It will try to deform continuously under the application of the external force, right? But in case of solid, it would definitely try to resist the motion, caused due to the application of this external force, as you can clearly see in this diagram. So if we have an object, say initially a cubical metal piece, I must say. So say if we and if we were to clamp the lower surface or the lower surface of this cube, and then we try to apply an force tangentially on its upper surface, you will see that the object will eventually go under some certain deformation with respect to its initial position. It will have some certain angular displacement, say with having some angle theta, say, and after some point you will see that the object does not deform any further, and in order to have further deformation, you need to apply additional force, right? So it basically means that if you had applied some certain force F1, say, the object will only deform up to a certain angular displacement, and beyond that it won't displace, because it is now applying an additional resisting force that is resisting the deformation of the object, right? And that is a fundamental characteristic of a solid. So it's basically the same. So if we deformation, as he has pointed out, Professor Gupta pointed out, it's pi by 2 minus theta 1, because this would be the actual deformation. So theta d would be pi by 2 minus theta 1, right? So deformation, and he also pointed out that the deformation is proportional to the applied shear force. That, as I already mentioned, the more force you apply, the deformation would be higher. But after a certain point, the object would stop deforming, and to deform the object further, you need to apply some additional external force, right? And that's why, and another fundamental concept is that this resisting force that resists the motion, resists the deformation of the object would be proportional to the net deformation. That is, higher the deformation, higher would be this resisting force. Okay, so but these kind of resisting forces we do not see in the case of fluid. Like as he Afridi rightly pointed it out, like if we were to give some tangential force or tangential force to the surface of the fluid will deform continuously under the application of this force without some additional without resisting the deformation of the fluid, right? But we can again see that even though the object is going on a deformation, it will eventually this deformed layer will eventually obtain a certain equilibrium velocity, right? Say if it is noted by v in this case, it will obtain some certain equilibrium velocity, and since it is obtaining some equilibrium velocity, there is and thus there is a resisting force that is being generated in the fluid, right? Though not resisting the deformation does not mean that there is no resisting force, right? Though the object is not resisting its deformation under the application of the force, it is eventually obtaining some certain velocity, right? Some certain uniform velocity, which basically tells us that it is having some certain resisting force that causes the deformation to reach some certain equilibrium state that results in a certain equilibrium velocity, right? So, and this resisting force that results in the generation of the equilibrium velocity is dependent not on the net deformation but a deformation rate, right? Like since we pointed out that in the case of fluid there is no resistance to the deformation, so there is no point of discussing what is the total deformation, right? It will go to be infinite, right? There is no scale to determine the net deformation due to the application of the external force. But the other parameter that could be useful in our case to quantify this resisting force that results in the generation of an equilibrium velocity would be the deformation rate, right? So in the case of fluids, it is the deformation rate instead of deformation that takes the central role in determining the motion of fluids under the application of some external forces. Okay, so this very nature of fluid is a key way to define what key way to obtain a definition of fluid, right? So as it is shown here, a fluid deforms continually under the action of shear force, but at a rate determined by the magnitude of shear force and the fluid properties. Okay, so this is a way by which fluid can be defined, right? It's a very simple or very simple but apt definition of fluid, and differentiates how it is different, and which differentiates it from a solid, right? So this is a very important concept which helps us to differentiate between the solid and fluid, but again also sets a way or shows us sets us in a direction towards which we can now try to quantify the parameters or the useful parameters that are actually being used in quantifying this fluid motion, right? So as I pointed it out, it is a deformation rate instead of net deformation. So for the fluid, it is the deformation rate. And for solids, it is net deformation. See, these things may seem very simple, but is quite fundamental and important. Like why it is the deformation rate instead of deformation for in the case of fluids, why it's important, and you will eventually see that uh, these deformation rates are fundamental in helping us to determine the shear stresses that act in the fluid, okay, which you will eventually see that is being determined by the Newton's law of viscosity. Okay, so because see, in the case of solids, I believe all of you may know the Hooke's law, or must have known about the stress strain diagram, right? So could anybody tell me about what's the Hooke's law is in the case of solids?
Modulus of elasticity.
Stress is directly proportional to strain up to elastic limit.
Right. So rightly, it's correct. It's rightly pointed out. And if you, okay, that's fine. So uh, that's the correct definition of Hooke's law. And the main objective for me to ask about Hooke's law was to know about the stress strain diagram, right? So in the case of solids, what is in the stress strain diagram? What is in the y-axis? Is it the stress or the strain?
Strain.
Y-axis.
Y-axis is stress.
Stress. Okay. And obviously the x-axis would have strain, right? So pointed out by epsilon. Okay. And as you rightly pointed it out, for in the case of, say, I am discussing about ductile materials. So up to certain limit, certain region, it would have a straight line. The stress is directly proportional to the strain. The stress is directly proportional to strain, and this point is known as the elastic limit, or like, if please ignore the wiggles in the line, like, I'm sorry, but up to this point, the elastic limit, the stress is directly proportional to strain, and after that the object, I guess it is again wrong, sorry. So to go and to have some, okay, so I guess it's how it works, it's how it looks like. So forgive me if I'm wrong, and obviously correct me if at all like I was wrong. I guess for the case of ductile materials, there are upper yield point, lower yield point, then point of ultimate stress, and then the failure point, right? And this is the proportional point, or the proportional actually is the proportional limit instead of elastic limit, but it's more or less the same. So let's not dive deep in it, but the main objective for me to go to Hooke's law and the stress strain diagram is understanding how, like, telling or making you understand how we deal differently with, in the case of solids or in the case of liquids, right? In the case of solids, I'm sorry, in the case of solids, and in the case of fluids. So in the case of solids, we are dealing, for understanding the characteristics or the properties of the fluid, we of the solid, I'm sorry, we are dealing with the stress strain diagram, okay, which is a standard concept that you will deal with in any of the standard material courses or any materials courses. You will learn about this diagram, so that's fine, because we are dealing with solids in that case. But in the case of fluids, the y-axis remains the same, okay, the y-axis remains the same, because stress is again a important parameter, or the important parameter in the case of fluids. But in the case of fluids, instead of the strain, it would be strain rate, okay. That's what differentiates the fluids compared to solids. Okay, instead of stress, it is the strain rate in case of fluids. Okay, that is what I wanted to that's the difference that I wanted to emphasize in the case of solids and the fluids. So I guess I was clear, and as you will eventually see that the Newton's law of viscosity tells us that the strain would be directly the stress in the fluid will be directly proportional to the strain rate, and there is no concept of any limit here. But Newtonian fluid is itself a very conservative case, I must say, in simple words, because they are not at all like, I would not say very less, but I would say not considerable amount of fluids that are Newtonian. Like there are many fluids in nature that are non-Newtonian and thus require a different way to tackle them. But still, for the case of simplicity, we discuss Newtonian fluids in most of the basic fluid mechanics courses. So in this course also we will discuss only about Newtonian fluids. So this is how the stress and the strain rate diagram of a Newtonian fluid would look like, which we'll eventually see in the later part of today's discussion. So I guess I was clear regarding differentiating between the fundamental characteristics of solids and fluids. Okay. Okay, so again, a fluid at rest or a fluid in uniform motion cannot sustain any shear force. So, okay, I've already written the answer. I thought to ask someone why is it so, but basically because to have a certain strain rate, there needs to be a relative motion of fluid layers, relative motion between the fluid layers. Okay, so I guess this is basic, so I don't think I must go discuss more about it, so that's fine. Okay, so this diagram basically shows is a example of a quiet flow where one of the plates is held stationary and other plate is moving, and it is the motion of the upper plate that drives the flow. Okay, see, in the later part of the course you will eventually see that there are various forces or mechanisms that drives the flow. Okay, or basically you can understand in a way that generates the flow, right? Because fluid cannot move by itself, right? It has to have some additional or external forces that results in the motion of the fluid, right? So in the case of quiet flow, since the upper plate is moving, the motion of the upper plate is what that generates the motion of the fluid, right? And thus it is the motion of the upper plate that drives the flow. So is that clear? Like what do you mean by the driving factor of a flow? It's fine, like if it's not clear, because it will only be clear. It will only be clear when we discuss different examples where we can see different driving forces that generates the flow. So in the case of pipe flow, it is the pressure gradient that drives the flow, right? So in the case of boundary layer, it is the inertia force of the incoming flow that drives the flow. So there are different mechanisms that can be a driving factor of a fluid flow. But in this case, in the case of coed flow, it is the motion of the upper plate or the moving plate that drives the flow or that generates the flow. Okay, so again, in this case, in the case of the coed flow, again I didn't write the entirety of the derivation because it was discussed very nicely in Professor Gupta's lecture, but still just to get a brief idea, in the case of coed flow, the rate of deformation is given by dvx by dy, where vx basically denotes the velocity in the x direction. The coordinates are given, so this would be vx. Okay, vx, vy, vz. Okay, or you can write as u, v, W. Another standard way of denoting the velocity in the different directions. Okay. See, this deformation rate is only valid in the case of co-ed flow. Okay, only for this kind of flows where the one of the plates is stationary and the upper plate is moving. It's not necessary that all kinds of flow that we deal with would have the deformation rate as this. Okay, it's only very exclusive to the co-ed flow, and thus the deformation rate is given by this, and this gamma dot represents the deformation rate. Okay, I used epsilon dot, but you can also use gamma dot. Okay, so that's fine. Only for co-ed flow, I would emphasize that, only for co-ed flow. Okay, but still this diagram can also help us to discuss some more fundamental concepts. So see, let me just because it's an introductory session, I would again like to I'd just like to discuss about the co-ed flow quite a bit, so that it is clear and so that it helps you to build the concepts for the further sessions, right? Because this is an introductory session, so I guess it's very fine for me to discuss even such simple examples. Okay, so just before starting, so do any one of you have read about co-ed flow before? Or this? Yes.
What, sir?
Now, have any one of you learned about co-ed flow before today? No, that's fine. Okay, then I will discuss it. Other than Afridi, like anyone else, like have you ever any one of you heard about co-ed flow before? Okay, that's fine. That's completely fine. It's a basic level course, but still, basic level course that deals with the application in as its fundamental objective. But still, it is no harm for me to discuss about co-ed flow for the introductory session. But still, okay. So in the case of a co-ed flow, what we basically deal with is motion between two plates. Okay, two parallel plates, and it's not necessary to be parallel. It can also be cylindrical, to cylindrical surfaces, and in the limit of a small elemental surface area, say, okay, co-ed flow could also occur between two cylindrical surfaces, and in this case these are known as Taylor co-ed flow, and in this case also you will eventually see similar velocity profiles. Like, say, if the outer cylinder is moving with certain angular velocity omega and the inner cylinder is stationary, here in this case also you will eventually see that similar velocity profiles are generated. Okay, so okay, just to be clear, because if I say only parallel plates, then you may think that co-ed flow may only occur between two parallel plates. That's not the case. It may also occur in cylindrical surfaces as well, and even in spherical surfaces. That are known as spherical co-ed flow, right? So let me not dive very deep in these kind of examples because they are far advanced topics. But as a fundamental or introductory example, let me just discuss about the co-ed flow in between two parallel plates. Okay. So in the case of motion of fluid between two parallel plates, what we consider is one of the plates is stationary, and in this case, as I mentioned, the lower plate is stationary. And the upper plate is moving with certain velocity v naught. Okay, and and the motion of the upper plate would cause the fluid to move, and the motion of fluid could be depicted by the help of this velocity profile as shown here. This is the velocity profile, and the velocity profile is generated as such that the velocity at the upper surface of the lower plate, which is stationary, is 0, and the velocity at the upper plate, which is moving at velocity v naught, is equal to v naught. Okay, obviously v naught relative to the velocity at the lower plate of the lower plate. Okay, so why does this happen? Like, before knowing that, had anyone of you known about the no slip boundary condition, or the no slip boundary condition? Yes.
Yes, sir. The relative velocity between the fluid particle and the wall should be 0.
Okay. Right, as rightly pointed out by Afridi, it is absolutely correct. So what happens is that the no slip boundary condition tells us that, like, if the fluid is moving within a confinement, okay, in this case also these two plates acts as confinement, and the relative motion between the fluid, or in simple words we can say that the fluid particles directly adjacent to the surface of these confinements tend to stick to the surface, and when the fluid particles close to the surface would stick, what would happen is that it would try to catch the velocity with which the confinements or the surfaces are moving, right? So in this case, since the lower plate is stationary, the fluid particles directly in contact with the lower plate, the velocity of the fluid particles relative to the upper surface of this lower plate would be 0, right? Because these fluid particles tend to stick with the surface of the lower plate that is stationary, so its velocity is 0. Okay, and the upper plate and the fluid particles that are in contact with the upper surface in the lower surface of the upper plate, that is in this surface, also stick with the surface of the upper plate, right? And thus relative to the motion of the upper plate, the velocity of fluid particles would be, anyone? Relative to the motion of the upper plate, the velocity of the fluid particles
will be 0.
Yes, absolutely correct. So relative to the motion of the upper plate, the velocity of the particles sticking to the lower surface of the upper plate, that is here, would be 0. But what we are interested is the relative velocity of the fluid particles relative to the stationary plate, right? So since these are stuck to the lower surface of the upper plate, these are now moving with a velocity v naught relative to the velocity of the stationary plate, right? These are moving with a velocity v naught relative to the velocity of the stationary plate, which is 0, right? So what would happen is that these upper layers, okay, these upper fluid layers are moving with velocity v naught, okay, or in simple words, moving with higher velocity. So what they will tend to do is, since these are stuck, it has a relative velocity 0, okay. As we move up, since the upper layers are having some certain velocity relative to the lower surface that is stationary, it would tend to impart certain momentum, okay, certain momentum, or in simple words, tend to cause the layers below it, like the upper layers, if it is moving with velocity v1 say, and the lower layer is moving with velocity vl, and v1 is greater than vl, so what it would tend to do is the layers having velocity v1 would tend to speed up the velocity of the fluid layer having velocity vl. Okay, so basically it would try, what the upper layer would try to do is it will try to speed up the motion of the lower layers. Okay, is it clear? Like, because it's very important. Is it clear?
Yes, sir.
Yes, thank you. So it will try to speed up the velocity of the lower layers, and similarly, since the lower layer is moving with a velocity lower than the upper layers, the motion of the lower layers will try to slow down the motion of the upper layers. Okay, it's just the game of different fluid layers moving with different velocities. Okay, different relative velocities. So, and thus as we move up, the velocity of these fluid layers will increase and eventually reach a value v naught. Okay, and as we go down, it will eventually reach a value that is that is equal to the velocity of the lower plate, that is 0. Okay, so vl is equal to 0. Okay, and this is in gist, or in a in a compact manner, this is how a coed flow is generated, or this is what the coed flow actually is. Okay, where the motion of the upper plate causes the fluid layers to move related to each other, and thus generating a linear velocity profile in this manner. Okay, so is it clear, like what is a coed flow? Or if there's any doubt, you can ask, because this is the only flow that we will discuss today. So is it clear, coed flow?
Yes, sir. Clear.
Okay, thank you. And others, like I'm only hearing from Afridi, other than there are Alex, Ishan, Vinod, Aditya, like, okay, I will assume that it is clear. So okay, that's fine. And okay, then I guess I will try to move it a bit higher pace so that we can cover up the concepts. Okay, so okay, someone saying something. Yes.
Sir, it is clear, sir.
Okay, thank you so much. Okay, so in a just some time before, like I asked all of you to tell me about Hooke's law, and Afridi or rightly pointed it out what Hooke's law is. So the stress is directly proportional to the strain within the elastic limit, right? So similar to that, the Newton's law of viscosity states that the shear stress in fluids are directly proportional to the shear strain rate. Okay, shear strain, okay, I did wrong, it should be rate. So it basically means that tau is directly proportional to lambda dot. So the proportionality constant in the case of Hooke's law was modulus of elasticity, right? Young's modulus of elasticity, and in this case it is the viscosity, or the dynamic viscosity, to be more precise. Okay, the proportionality constant in the case of Newton's law of viscosity is the dynamic viscosity. Okay, right, and in the case of coed flow, we saw that the deformation rate is given by this, so we can take, if we substitute it by that, we can write as tau is equal to mu dvx by dy. Okay, not applicable universally. Again, this relation between the stress and the strain rate is not applicable universally, and is only applicable for Newtonian fluids. Okay, so these are the units values. I guess it's not that important, but What is more important for me to tell is about the applicability of the Newton's law of viscosity, okay, and the Newtonian fluids. Okay, so I guess okay, discussed. I don't think since like many of you don't know clearly about coed flow, I don't think this example right now would be a good way to discuss, because this is unsteady case of coed flow. But I feel that this is not wise for me to discuss right now, like how these profiles are generated. But okay, that's fine. So other than that, I guess it is okay. So I would like to discuss a bit about Newtonian and non-Newtonian fluids. Okay, so this is something that I guess it was not discussed in the lectures, but I would like to point out because it's important. Is something known as the constitutive relationship. Okay, constitutive relation or relationship, whatever you say. It's a constitutive relationship. Okay, so what it basically means is it is the relationship between the stress and the strain rate in a fluid. Okay, in the case of solids it would be stress and strain. So in the case of fluids it is simply the relationship between stress and strain rate. Okay, see why it is important, because for our case, or what we are going to discuss now, what we are going to primarily discuss in this course, we discuss a linear relationship between the stress and the strain. Okay, given by this. Okay, but it is not necessary that again sorry, so it is not necessary that this is what to say, universal relationship. There can also be cases where the stress may be related by relations of this form. Okay, which may not be linear. It can be parabolic, cubic, and can have even fractional values. Okay, why I am discussing about this? It's because to just to let you know about the extent of the subject that we are going to not touch, right? Because these are types of fluid that constitute a vast variety of fluids. Okay, vast variety of fluids. And these are only for Newtonian fluids. And for the context of this course and most of the basic, or I must say most of the fluid mechanics course, we basically deal with Newtonian fluids, and thus the outcomes, or thus its outcomes, such as the Navier-Stokes equation. Like I guess you might have heard about it, the Navier-Stokes equation. That is the equation that governs the all kinds of fluid flow. Okay, so a Navier-Stokes equation is an outcome of an assumption that the fluid that we are taking into consideration is Newtonian. Okay, so Navier-Stokes is only applicable for Newtonian fluids. The moment we deal with non-Newtonian fluids, the Navier-Stokes equations fails to determine its motion, and we again go back to a more fundamental form of equations that is known as the Cauchy's momentum equation. Okay, Cauchy's momentum equation. So these are not the things that we emphasize much upon in this course, but just since it's an introductory session, just to let you know the extent of which the fluid mechanics course actually deals with in our day-to-day life, and what and the extent up to which we actually read, the vast difference in it. So just to tell you about that, so the constitutive relationship, okay. So that's what I want to discuss about. And okay, so depending upon the relationship between the stress and the strain rate, there can be different kinds of fluids again, okay. So the most common that we are going to deal with is the Newtonian fluid or the Newtonian fluids, and the most common example is water. And since water constitutes a vast extent of our earth, and it has vast applications in our day-to-day life, so we can say that knowing the nature of Newtonian fluids would help us to deal with most of the fluid flow problems. But if you are going to planning for research or in different fields other than engineering fields, then I guess I must say different kinds of knowing the characteristics of different kinds of fluids rather than a Newtonian fluids also becomes necessary, okay. One of the most famous fluid or important fluid that is not Newtonian is blood, okay. And thus the motion of blood through our arteries, veins, even though it's complicated because of the expansion and contraction of our veins, even if we take that into consideration, the very nature of the fluid that is non-Newtonian makes it very difficult to attack such kind of problems, right? Because the fluid itself is non-Newtonian. Even if the equation that we're handling, the Navier-Stokes, is unsolvable, even that unsolvable equation is not applicable for such kind of flows, and thus the difficulty in understanding the nature of the flow of blood in our veins or arteries, okay. That's what the difficulty that we usually face in the medical field, and thus the extensive research in the domain of non-Newtonian fluids is necessary. So did anyone say anything? Oh, okay, that's fine. Okay, so again I briefly discussed about the Reynolds experiment. I would suggest that you look into the Professor Gupta's lecture. There it's very nicely shown through the proper diagrams and animations, where basically the experiment was done to differentiate or let us know about the two different kinds of flows depending on, that is, the laminar and turbulent flow, okay. So before discussing that, could any one of you please tell me the difference between laminar flow and turbulent flow, or if any one of you has learned about it or known about it before, laminar and turbulent flow? Yes.
In laminar flow, the fluid particles do not cross each other's, like does not intersect each other.
And in turbulent flow?
In turbulent flow, the particles move in random direction, thus intersecting each other, their line of action.
Okay. Yes, so it's I'm sorry. So it's a good definition, or I must say a proper definition or appropriate definition for an introductory session. So as you pointed out, that fluids in the case of laminar flow move in laminar, or is derived from a word called laminates. And if you know laminates, it basically means sheets of object, right? Sheets. So it basically means that the fluid would move in distinct sheets or layers, or in the case, or in a more proper way, I would say in a move in layers in uniform motion, and there would not be any momentum transfer. So as you were telling about intersection of line of action, rather than it, I would say there would not be momentum transfer or extensive momentum transfer between these fluid layers, okay. There would not be extensive momentum transfer between these fluid layers. But in the case of turbulent flow, there would be extensive momentum transfer between these fluid layers, and thus it would result in an irregular motion of fluid particles, and thus the laminar nature of the flow would vanish, and thus would result in a very chaotic and irregular motion. A turbulent flow in itself is a very what to say is a very deep concept and requires certain characteristics to be fulfilled for a flow to be turbulent. So I will not dive deep into that right now, but in simpler version I could say a highly irregular flow with extensive momentum transfer between the fluid layers that eventually results in the irregular motion of the fluid. Okay, that is known as turbulent flow. So what Reynolds did was, in his experiment, he used a dye in a pipe flow and tried to see the motion of the dye by varying different parameters in the pipe. So what are the parameters that it could change? First was the dimension of the pipe, or okay, even the easily what he could change is the velocity. Okay, the velocity with which the fluid moves within the pipe, that he could change, right? So I would say velocity is one of the parameters that he could change. Again, he could change the diameter of the pipe. Then he could change the very properties of the fluid that is being flown within the pipe. So I must say the density and the viscosity. So what he found out that the nature of the flow in the pipe was determined not only by the was not only affected by the each of individually by these parameters, that is velocity, okay, that is velocity, dimension and the fluid properties, but was actually a composite parameter, or in our case luckily a non-dimensional parameter, which determined the transition of the flow from laminar to turbulent. And this non-dimensional parameter composing of these flow properties are known as flow and system properties, and is known as the Reynolds number, which is given by rho VL divided by mu, where mu is the dynamic viscosity. Okay, and another definition of Reynolds number is the ratio between the inertia force and the viscous force acting in the fluid flow. Okay, so now if we look into the case of the swimmer and the bacteria, okay, just for that case, just recalling that case, if you were there from the start of the lecture, I guess many of you were there from the start of the lecture. So I said that in the case of swimmers, the inertia force dominated. I would say IN and VI, inertia force dominated. So, and in the case of bacteria, it was the viscous force that dominated. So just by intuition, okay, just by intuition, can any one of you please tell me in which case the Reynolds number would be higher?
For swimmer.
Yes, it's very I must say very fundamental and very easy to see. Like, since the numerator that consists of the inertia force, and I told that it is the inertia force that dominates the motion of swimmer, so the inertia force dominates the motion of the swimmer, and in this case, since it is much more dominant than the viscous forces, the Reynolds number in the case of swimmer would be much more higher in the case of the motion of bacteria, where it is a viscous force that is in a denominator that dominates the motion of the bacteria in that fluid regime, right? And thus the RES, or the Reynolds number of swimmer, would be much more greater than the Reynolds number of the bacteria. And in the case of the motion of bacteria, where the viscous force are dominated, such kind of flow have a special name known as the creeping flow or the creeping flow regime. Okay. Okay. Then I guess. Okay. So I feel for the introduction session, I would say I would like to keep it up to here. We will for the next session we will discuss a bit about the laminar and turbulent boundary layer, and then the consequent topics that follow, and then the topics of the next week. Okay, and then also I would like to go a bit faster in the next session, like not diving deep in all the topics, because I will essentially assume that you have attended the lectures of Professor Gupta, which are much more better and clearer than this session, which I am trying to keep, because the fundamental of taking these sessions are trying to help you with the doubts that you may have after attending Professor Gupta's lectures, and thus discuss some problems. So this is the fundamental objective of having these sessions. I'm sorry, but since this was an introductory session, I thought that it would be better to start with some concepts, so that you can get an idea or taste of what we are going to deal with in the later part of the course, and just to welcome you all in a way that you may find it interesting. And I hope that with the discussion of so many topics, so many interesting topics and examples, I hope that you might have found this session very interesting. And obviously I request you to attend the lectures of the next week, and also try to solve the problems for this week's session. And since we have not discussed the problems from this week, I would be very welcoming to discuss the problems of this week in the next week's session also. Like if you have any doubt in solving the problems of this week's session, we can discuss it in the next week. So okay, and again, you have a problem solving session on 31st, I guess on Sunday. So I would encourage all of you to attend that session also, so it would be much more clear for you. And again, I request all of you to properly see the lectures of Professor Gupta, because they are the best resources for us to learn. Okay, so I guess I will stop up to here. There are much more concepts, laminar boundary layer, turbulent boundary layer, and for that you need to understand what a boundary layer is. So this will take a bit more time, I guess, which will not permit us within today's session's time frame. So I request you to look at the lectures, and if possible, since it is an application based course, both Professor Gupta and we assume that you know some of the fundamental concepts, if not all, but some of the fundamental concepts of fluid mechanics beforehand, so that we can emphasize more on the applications rather than the fundamental concepts, right? But still, if you don't know, it's completely fine. I encourage you to take any of the fluid mechanics book, just go through it, look in the fundamental concepts, at least know what is what. Then at least we can help you to understand or help you to clear your doubts, so that the session could be completed within the required time frame and covering the required topics. Okay, so I hope you don't mind, and thank you everyone. So thank you for attending today's session. So if you have any doubt, you can. Yes. Okay, so if you have any doubt, you can ask up to today's session, for today's session. If not, then you may leave. So thank you. Yes. Thank you, Alex. Thank you. Okay, then I'll be ending the session, I guess. It's fine. So okay.